Okay, we are ready.
Okay, give me a second. It's all good?
Yeah.
Okay. Okay, let's get started. Okay. Okay, welcome everyone. We're starting the Safari Live Seminars for 2024 with a Safari veteran, Giray Yağlıkçı, Abdullah Giray Yağlıkçı. Giray is going to present part of the work he's done in his PhD. He's going to present the next part next week. I think 5 days later.
Yes,
something like that.
Come on.
Yeah, I call Giray a Safari veteran because he's gone through many stages of Safari. He was an intern and many different locations of Safari also. He was an intern at Carnegie Mellon for about a year or so, where he did exciting work. And then he came and joined as a PhD student at the ETH. And he's at the very end of that journey, at least the PhD journey right now. He's going to graduate hopefully next month. I have a draft of his thesis. And what you're going to hear about is going to be his part of his PhD thesis. And I'll leave the floor to you. Feel free to ask questions. Someone will monitor the questions on YouTube, so we can convey them to Giray. Giray, go ahead.
Thank you. Thanks for the kind introduction. Okay, so today we will talk about a deeper look into RowHammer's characteristics. So this is roughly half of my thesis. I hope I will get through all of them without boring you. We will be looking into DRAM devices, in long name dynamic random access memory. So in many of the smart devices in our daily life, we deal with a great amount of data, and this data is stored in DRAM chips. And therefore, for these systems to work reliably, secure, and safe, we need to trust these DRAM devices because our data is there. So I will give a brief introduction of how DRAM is organized and how it operates. So this is an example picture of a DRAM module. It has multiple chips, as you see. And within each chip, we have multiple banks. And then within each bank, we have several subarrays. And then within each subarray, we have a two-dimensional array of DRAM cells. Each of these circles is a DRAM cell. And these DRAM cells are organized as rows and columns. So when we want to access data in DRAM chip, we access data in a DRAM row granularity by asserting these blue lines called word lines. And then these cells are connected to a structure called row buffer through these orange vertical lines called bit lines. So this is a DRAM cell on the right-hand side. We have an access transistor and a capacitor. So the data is stored as an electrical charge on the capacitor, and there are multiple charge leakage paths in the circuitry. So it is a volatile kind of memory. So if you wait long enough, you lose your data. And for that, we need to perform periodically some operations called refresh operations that restores the lost charge on the capacitor back. When we want to access data in DRAM cells, first, we need to activate the row and fetch the row's content into the row buffer. And then we perform accesses in finer granularity called column accesses from this row buffer. And then once we are done with the data in that row and we want to activate another row, we need to first pre-charge the bank so that the row is not connected to row buffer anymore, and then activate another row. So this is a essential part of how DRAM operates, and it comes with this RowHammer vulnerability issue. So this is shown in many times before, but I will just go through this animation. Let's say you have some data in row 2, and you open this row by activating this word line, and then you close it. And then you do this many times. If you do it many times, then you can induce bit flips in the adjacent rows, physically adjacent rows. And this phenomenon is called RowHammer. You basically hammer a row, and then you induce bit flips in the nearby locations, and it essentially breaks the memory isolation, which is a fundamental safety and security primitive, so that you can change the data without accessing it. And that data might not belong to you even. Okay, so when you do this many times, you have many bit flips around the chip, and for terminology, we call the row that we keep hammering as aggressor row, and the other rows that are affected as victim rows. So I'd like to give a swimming pool analogy. So as you can see, there are like swimmers here, and there are separate lanes. And the swimmer in the middle, if that person swims aggressively, it can splash water or create some waves, right? And then it can create some disturbance in nearby swimmers. So this is some analogy that I like to explain how RowHammer works internally. And yeah, so RowHammer is a prime example of DRAM read disturbance. So this phenomenon can be exploited in many ways. It can cause data loss or corruption. It can compromise application correctness because you can induce bit flips. And by using RowHammer, you can leak private information from other users, and you can even take over a computer. And there are many prior works actually experimentally demonstrate that this is feasible in real systems. Another aspect about DRAM read disturbance and RowHammer is the technology scaling. So as the technology node shrinks, the size of DRAM cells get smaller, and also DRAM cells get closer to each other. And then once we hammer some rows, we induce more disturbance, basically, nearby them. So this read disturbance phenomenon get actually worsened with technology node scaling. And as a result, the existing mitigations for this phenomenon get prohibitively expensive. And we need more effective and efficient solutions for reaching or having some reliable, secure, and safe systems. There's an increase in the interest in academical domain for understanding, exploiting, and solving RowHammer. So we have increased the number of papers published every year. I will not get into literature too much, but I'll continue with this thesis statement. So all my works in this thesis are oriented around this statement, building a detailed understanding of DRAM read disturbance and leveraging insights into DRAM chips and memory controllers enable us to mitigate DRAM read disturbance efficiently and scalably. And we will focus on the first part today, building a detailed understanding of DRAM read disturbance, and then we will focus on the leveraging insights into DRAM chips and memory controllers in the next talk. To study this topic, I did several studies on providing a detailed understanding of DRAM read disturbance. So this is the focus of today's talk. So for a deeper look into RowHammer's characteristics, we looked at the effect of temperature on RowHammer, memory access patterns, some victim cells' physical location, and voltage. And then we also studied how we can solve this DRAM read disturbance, and then we proposed mechanisms that throttle unsafe accesses, parallelize some preventive actions so that preventive actions come at lower cost, and leveraging the heterogeneity in the chip so that we can perform these solutions in a more efficient way. But this is not the focus of today's talk, as I said earlier. And this is the just advertisement of the other talk that we will look into these solutions. Okay, so this is my outline today. We will look at every single one of these: temperature, memory access patterns, victim cells, physical location, and voltage. Before going into the results, I'll talk about the methodology a little bit. So this is our experimental setup. that we report in our papers as a modified version of SoftMC. Today we call it DRAM bander, and you can see the reference down there. So here we have a power supply on the left. Actually, I can go with the animation. So we have an FPGA board programmed with DRAM bander, and then we have a DRAM chip actually connected here, and we press some heater pads on this DRAM chip so that we can heat up the DRAM chip to the temperature that we like. And there's a temperature controller that ensures that the DRAM chip is at the temperature that we want it. And there's a power supply here that we can change the voltage of the DRAM chip. So this infrastructure gives us fine-grained control over DRAM commands, timing parameters, temperature, and wordline voltage. I will talk about wordline voltage in a little bit. So to characterize our DRAM chips for the worst-case conditions to the best we can do, we prevent sources of interference during the core test loop. To do so, we disable DRAM refresh operations so that we avoid refreshing the victim rows, and we disable DRAM calibration events so that there is less variation in the test timing. And we also disable RowHammer mitigation mechanisms to observe the circuit level effects of our tests. And we test, we conduct our tests in a short amount of time so that our bit flips do not include the data retention bit flips. And we repeat our tests multiple times and get reliable data out of that. And as the default access sequence, we basically follow the methodology provided in the prior work, which is repeatedly accessing two physically adjacent rows as fast as possible. And then we alter this memory access pattern when we want to see the effect of memory access patterns. Okay, so so we test different DRAM chips in it's in total 272 DRAM chips in total that are coming from 4 major manufacturers, and they implement 2 different DRAM standards, and they implement different variations of density, die revision, and chip organization. And in individual papers, you can see actually detailed information about these chips that we tested. So let's move into the results on temperature. So I'll start with some key takeaways. So the first takeaway is that to ensure DRAM cell is not vulnerable to RowHammer, we must characterize the cell at all operating temperatures. And the second one is the RowHammer vulnerability, or DRAM read disturbance in general maybe, tends to worsen as DRAM temperature increases. But there are some individual DRAM rows and some chips even that exhibit the opposite behavior. So this is a high-level representation of the effect of temperature in a cartoonish way. So on the x-axis, we have the temperature increasing from left to right. And just imagine that on the y-axis, there's some metric that identifies the vulnerability of to the DRAM read disturbance for a given DRAM cell. And we observe that as temperature increases, the vulnerability of a DRAM cell first increases and then decreases after some temperature. So we observe that DRAM read disturbance is actually more effective within a bounded temperature range. And this bounded temperature range can be different across different DRAM cells. So here comes the first key takeaway. A DRAM cell should be tested at each possible operating temperature to ensure that it's resilient to read disturbance, or it's vulnerable to read disturbance at a given condition.
Are you going to explain why this is the case?
Yes.
No, if you're going to explain it, you don't need to explain it now.
So these slides don't get into the circuit level phenomenon, actually.
Yeah, maybe you can explain that.
Yes. So we observed the same behavior in one of the error mechanisms that is presented to explain this DRAM read disturbance, which is the trap-assisted error mechanism. To my understanding, it's like when you have temperature at some cold level, the electrons are not really have great mobility, so they don't move to the extent that they will create some, they will get stuck at some traps, and then they will cause bit flips. And as you increase temperature, they get some mobility. They get into those traps, but after some temperature level, they can just like go really fast and without getting into those traps. And then you basically end up not having electrons stuck at those traps. So this is my understanding from that model, and it also shows that in some bounded temperature range, you have some local maximum of maybe global maximum, I'm not sure, of this read disturbance, and yeah, that's the way.
And you observe that consistently, this particular temperature range for a given cell consistently across many experiments?
Yes, yes. We repeat our experiments at several temperature levels many times, at each temperature level many times, and then we observe the same behavior reliably. And I will show some more results about that as well.
Okay.
Okay. So this slide is explaining exactly what I was talking about actually. So as you increase temperature, there is a lower bound and an upper bound. In between, you observe bit flips, and then outside of this range, you don't observe any bit flips. And we call this range as vulnerable temperature range. When we look at the fraction of the vulnerable DRAM cells that experience bit flips in a vulnerable temperature range, we look at if they experience bit flips in every single temperature point we test in this vulnerable temperature range, and almost all of them have this vulnerable temperature range as a continuous temperature range. So once they start observing bit flips after this lower bound, they keep observing bit flips until they reach the upper bound, and then once they reach the upper bound, they stop observing bit flips. So as a result, most DRAM cells are vulnerable to RowHammer throughout a continuous and bounded temperature range. So this is a population density kind of plot. So in the x-axis, we have the lower bound of this vulnerable temperature range, and on the y-axis, we have the upper bound of this vulnerable temperature range. And the color scale shows the fraction of vulnerable DRAM cells, and within every small rectangle over there, you see the fraction of the DRAM cells that fall into that region. So I will give two examples of how to read this plot. So for example, this 0.4% is annotated here. So it shows that 0.4% of the tested DRAM cells are vulnerable from 55 degrees Celsius to 60 degrees Celsius. And they're not vulnerable beyond these limits. And here, for example, 0.5% of the tested DRAM cells are vulnerable from 70 to 85 degrees Celsius. And as a result, we observe that different DRAM cells are vulnerable to RowHammer within temperature range that are specific to them. So this vulnerable temperature range also varies across different DRAM cells.
I'm sorry, Giray.
Yes.
Are these numbers consistent among all the different DRAM chips you tested?
No, the variation changes from chip to chip and from manufacturer to manufacturer.
This is one particular chip?
This is an aggregated result for manufacturer C.
Okay.
Which is Hynix.
When their manufacturers look, their chips look similar? This manufacturer's chip looks similar in terms of this profile?
I need to double check the raw data, but I believe so. Yes.
I think it's good to have like pictures like this for each chip.
Yes, yes.
Can I ask one question? Why there's a sudden jump between 85 degrees to 90 degrees? Is there any insights on that?
85 to 9. What?
So when you check the upper bound, in 85 degree, up to 85 degree, at most you see like 3% 4%, but up.
Yes.
There's a jump.
Yeah. So we basically test between 50 degrees and 90 degrees Celsius. So we do not test 95 degrees Celsius. So the population that accumulates at 90 degrees Celsius on top actually includes the cells that will go to 95, 100, 105, right?
Okay. Now I
It's just because of our methodology.
So how do you know what is the actual upper bound temperature?
Well, we do not know, but this is basically a reasonable upper bound for operating temperatures.
Okay.
So you usually don't go beyond 80, actually.
But what is the maximum supported temperature for these chips?
I believe for these chips, it should be like 95.
Okay.
Yeah.
And do you need to increase the refresh rate between 85?
After 85, you need to increase the refresh rate. Other questions?
Are you sure there are no retention errors slipping into that type?
Yeah.
into the
So
top?
when you increase the refresh rate, actually you need to refresh every 32 milliseconds, and our tests are shorter than 32 milliseconds. We also test if when we conduct our tests, we first we know exactly how much time it will take for a RowHammer test. And the first thing we do is we just wait without hammering for the exact same amount of time. So we observe if there's any retention bitflip or not. And then since there's no retention bitflip, we conduct the test. Okay, so this is the plot for all manufacturers, all 4 manufacturers that we test. And we observe that up in the upper left, we have some great fraction of DRAM cells. So these cells are vulnerable to RowHammer at every single temperature that we test, from 50 to 90. So they can be even vulnerable, like below 50 or beyond 90. So we do not know that. But yeah, so they are vulnerable to RowHammer at all tested temperatures. And when we look at the diagonal, it shows us the points that are vulnerable to RowHammer only at that particular temperature. So I guess there's an example here. So for example, this particular cell that says 0.2% of the cells are vulnerable to RowHammer only at 70 degrees Celsius. We do not observe bitflips at 65 or 75 degrees Celsius.
How many times do you repeat these experiments?
10 times.
10 times.
Yes.
And you never see a bitflip in another temperature range.
Yes.
And you always see a bitflip in that temperature range.
Yes.
In all of these. Okay.
Yes.
Sorry, right. Does it mean that it is not possible to have RowHammer's attack below 50 degrees?
No, it's just like we didn't test below 50 degrees.
Okay.
So whatever we see here, like in this here, for example, 4.8%, right? So those cells can be vulnerable to RowHammer in lower temperatures as well.
Oh, for the same reason before.
Yes.
Okay.
It's just like we didn't test that range. And the reason is that the temperature was not really stable below that range because of the limitations in infrastructure. So we didn't have cooling, we only had like heating.
Okay.
Yeah. But it's important actually. It's especially people talk about cryogenic temperatures, for example, for getting rid of the DRAM refresh completely, as data retention time increases a lot when you go to colder temperatures. And it would be an interesting study actually to see how RowHammer is affected. Now we also have RowPress. I will talk about it later as well. But yeah, so for both of them, it would be interesting to see.
So what is the average temperature of a DRAM chip?
I think it depends on how much you pressurize it, but it's around this range basically. So when you just start, maybe you see like 40 degrees, but then when you start using it, after boot, so it can easily go to like 50, 60.
Okay.
Yeah.
Okay, thank you.
Okay, so next we look at the as temperature increases, how does the overall bit error rate changes? And this plot shows exactly that. And we observe that as temperature increases, the variation in bit flip counts per DRAM row actually increases. So more cell experience bit flips as temperature increases. So 0%, so everything is normalized to 50 degrees Celsius. So we basically see the delta on the y-axis, and increase in trend means that we have more bit flips as the temperature increases. And when we repeat this for all four manufacturers, so we observe in 3 of them that temperature, the bit error rate increases with temperature, but on manufacturer B, DRAM chips from manufacturer B show the opposite behavior, and we believe that this is because the DRAM size characteristics change a lot based on your design and manufacturing technology, and a lot of things that you might be doing during the manufacturing process, and because of that trap assisted error model that I talked about earlier, the DRAM cell can be like this temperature range for those particular DRAM cells can be fallen into the left side or right side of that curve, so that maybe the worst temperature for manufacturer B is somewhere in like 20 degrees, for example. And for other manufacturers, maybe the worst is above 90 degrees. So we do not know this, but this is just like we hypothesize like this. Yeah.
Good question. Can you explain the local dip on manufacturer C?
At 70 degrees? Yeah, it's still a mystery. We actually looked into that data. Yeah, the only thing we found about that is, so we conducted tests first at 70 degrees, and then we started sweeping for the other temperatures from 50 to 90. But yeah, I don't have a good answer for that, unfortunately. So we observed that the DRAM rows bit error rate can either increase or decrease based on the temperature, and it depends on DRAM manufacturer as far as we can see.
Can you go back?
Yes.
On manufacturer B, who's manufacturer B?
Samsung.
Okay. This is aggregated over all modules, right?
Yes.
And all modules look like this?
Yes.
Okay. Yes. Yeah, this is why I think it's good to see module by module pictures also.
Yeah.
Okay. Interesting.
Yeah, I'll try to gather it up.
Yeah.
And the error bars actually show the variation across like all rows in all modules. Okay. So it's quite consistent there.
Okay. Can you go back to, in light of this, previous one more.
This
one? So I'm looking at manufacturer B here. I see. The numbers here also kind of check out. So manufacturer B has the lowest numbers on top, let's say, compared to other manufacturers.
Yeah, you can say that, yes.
Especially compared to the left side, right? So if you look at the bottom left point, it's 7.0%. If you look at the top right, it's 4.something3%.
Yeah.
Whereas it's the opposite in all of the other ones.
That's right.
Okay.
It has to check out because
okay, I know, it's the same data, but
yeah.
Based on this, I was going to declare some victory, but I guess you cannot declare victory easily. So the victory that I wanted to declare was, anyway, I'm not going to go into that now. We can discuss it later.
Okay. So we also checked how the minimum activation count to induce a bit flip changes that we call HC first. This is the first hammer count to reach to the first bit flip. And we observe that it can change both ways depending on the manufacturer. And it tends to generally decrease, meaning that it gets worse as temperature increases. And as we have a larger delta in the temperature, the delta in the HC first also gets larger. And you can find more detailed analysis or information on this study in this paper. It was published in Micro 21.
Okay, can you go back? Somebody else had a question here.
Yes.
So is there any correlation between retention failures and RowHammer failures? Because in retention, it's also increases when the temperature increases, right? Do you have any data?
So in the study, we didn't look at that for these particular chips. Later on in RowPress paper, actually, that was tested, right? And that paper shows like very little intersection in DRAM cells that are vulnerable to data retention and RowHammer at the same time.
Ah, I see.
I mean, original RowHammer paper showed that also.
That's true, yes.
Yeah. But here, the temperature dependence is not strong at all.
Yeah.
It's very weak, I would say. There's some dependence clearly. But with retention, you can easily say that as you increase temperature by, let's say, 10 degrees Celsius, you double the retention areas. I think that was the formula that we showed in our ISCA 2013 paper. Whereas here, you cannot say anything like that.
It's not really that straightforward here.
Yeah. Here, it's very much dependent on the cell.
Yeah.
Yeah, I was going to ask a different question though.
Sure.
HC first tends to generally decrease. It's very hard to parse this.
Yeah. So it tends to generally decrease because in some cases it increases. It's similar to this opposite behavior of Samsung modules in bit error rate. So as temperature increases, bit error decreases, bit error rate decreases, and HC first increases in their case.
Okay, interesting.
Yeah, because the RowHammer vulnerability
reduces.
Yes.
Is this behavior related to the characteristics of those charge traps?
Yeah, so we think so, yes. It's just like, I don't have a proof, but that's my hypothesis.
Okay, thanks.
Should I move on?
So what is the temperature change you're referring to? This is the intervals. What is delta T?
So you jump from like 55 to 65, 70, for example.
Okay. Okay. Yeah. So you test HC first at different temperature levels, and delta T is the delta between those temperature levels.
So it was just a statistical analysis that we did at that time.
Okay.
We don't really like test at one temperature and then jump to a very high temperature and then test again over there. It's just like while sweeping temperature with 5 degree steps, we collected all of data and then we did some statistical analysis.
Okay.
Well, it's yeah, in observation 6 actually we need to rephrase that. It's not really based on delta T, it's based on temperature over there.
Yeah, that's why I'm confused over here.
In observation 7 actually it's more about delta T.
Yeah.
Do you think this varies with temperature or the rate at which temperature varies?
Which one?
The bit flips or this minimum activation count, these experiments. For example, if you suddenly cool or suddenly heat,
Yes.
or if you gradually do something, do you think there would be a difference?
It's hard to say without trying.
Okay.
So you're talking about like shocking the DRAM chip in a way, right?
Yeah.
Suddenly it's cooling down.
Yes.
We didn't conduct such studies, so
okay. Thank you.
So you're saying the second statement is it's not as temperature change increases, but as temperature increases.
As temperature increases.
I think it's good to look at it a little bit more.
Which part?
I have some. Maybe we can discuss later. But this,
Okay.
I think observations 6 and 7 are very tough to understand.
Yes, we need to rephrase
just by flashing it to the
yeah.
listener. The observation 5 I understood, but 6 and 7 are hard.
Yeah.
Without showing the data in a curve, right?
Yes. They were hard in the camera as well.
Yeah.
Okay. So this is the paper. We can find more results over there. And I will move to memory access patterns. So we looked at...
Before you move on, maybe
yes.
I'll challenge you a bit.
Sure.
So you have all these temperature results, which look interesting. What can I do with them?
I will talk about some applications at the very end, actually.
Okay, I see. So you're not going to do it right after you show the results.
Yes.
Okay.
That would be a better flow, maybe.
I don't know. I think it's good to think about it. But other people who may be listening may be having the same question, so they should wait until the end.
I can maybe mention a few things very quickly. So one thing you can do is you can spy on temperature, and then there's actually a follow-up work that we show that you can do that. You can, for example, if you want to attack a data server, for example, so you can identify the peak hours, peak time for the data center's usage by just measuring or seeing the change in RowHammer bitflips, if you can conduct RowHammer bitflips, and then you can time some other attack like denial of service, for example, to that time that's when the temperature is high. So you can use it for that purpose. So for defenses, for example, you can measure the temperature by using sensors and then retire some rows.
At that temperature?
Depending on if those rows are vulnerable to temperature, vulnerable to RowHammer at that temperature, you can retire them, deallocate. I don't know. Yeah, you can do things like that.
Yeah, I think it's interesting. So, but you're going to talk about those later.
Yes.
Okay.
I will not really cover everything, but I will mention them.
I like it, so I hope you cover it.
Okay.
I mean, the attacks seem a bit harder with temperature, but defenses maybe easier because the defender has better access to temperature information, and they don't need to conduct a RowHammer attack to defend, right?
That's true.
Whereas attackers, if they can actually conduct a RowHammer attack, maybe it's not that interesting to deal with temperature-related issues, right?
Yeah. So basically, you can sacrifice some capacity. You can choose to not to use some of the rows based on their vulnerability level, and then you can avoid read disturbance with flips. Yeah. Or you can dynamically tune the aggressiveness of your defenses based on the temperature as well.
Yeah.
Okay, so in memory access patterns, we looked into something particular. Actually, we didn't cover all the memory access patterns possible. So a quick recap of RowHammer access pattern is you open this row and then close it, and then open, close, and then you have bitflips, right? So here what we did is, what if we keep an aggressor row active and just stand there for a longer time before closing it? And we also did the opposite. We closed the row and then waited for a long time. So what we see is that read disturbance is actually more effective if the red memory region stays active longer. And by changing the access pattern in this way, actually, we can reduce the minimum amount of activations we need to perform by 36% based on our results in this paper. But later on, actually, this analysis paved the way to a deeper exploration of this phenomenon, and then it led to another paper later on that house on that. So our observation here was like fewer reads cause a more significant read disturbance when the read memory region stays active longer. So here is the baseline access pattern. So we activate the row. Let's say we have 2 rows that we keep hammering. We activate row A, and then after some time, there has to be a minimum amount of time that we need to wait. We close the row, and then after some time, we activate the row B. And then it goes like this. And in the first access pattern that we tested, we basically increase the time that both row A and row B stays active. And then in the other test, we basically increase the time in between 2 activations where the bank is pre-charged. So we observe that when we look at the number of bit flips per DRAM row, it increases with the aggressor row active time. And this is a quite straightforward relation, actually. So you keep your aggressor row active longer, more DRAM cells experience bit flips. And this is a common pattern across DRAM chips from all manufacturers. Okay, so in this case, we look at the minimum activation count to observe a bit flip. So here, lower is worse. So lower means read disturbance is exacerbated. And as we increase the aggressor row active time from 34 nanoseconds to 154 nanoseconds here, we observe that there is a decreasing trend in the minimum activation count to induce the first bit flip. And this is also consistent across DRAM chips from different manufacturers. And we conclude that as the aggressor row stays active longer, more DRAM cells experience bit flips, and they experience bit flips at lower activation counts.
Sorry, I have a question. Is there, I mean, when a certain region of the DRAM is used frequently, is it more vulnerable to RowHammer attack? I mean, when, for example, when your operating system is using some region, the DRAM very often, is that region also going to be more prone to RowHammer attacks?
So, so if you're talking about the vulnerability in the circuit level, it depends on the circuit's physical characteristics mostly, and it's about like density and how much the interference can affect across cells and things like that. But that thing you can observe that thing in system level in a way that if there's a process that keeps accessing to some particular region in your memory, maybe that process is already like activating a lot of rows in that region. And on top of that, if you conduct some RowHammer attack and then you also activate the same rows for some time, then maybe you can achieve some bit flips quicker compared to the other regions.
Okay. So maybe if I want to perform a RowHammer attack, selecting a region that is already accessed many times can make my attack easier, right?
It could work in that way. I will also talk about the special variation of RowHammer vulnerability. So not all DRAM cells are as vulnerable to RowHammer as the others. So I guess you need to be also lucky that like frequently used region is also a vulnerable region.
No.
Yeah, okay. But yes, that's possible.
Okay, thank you.
Okay. So about the access patterns, we also looked at the how much the increase in the bank pre-charge time affects the second access pattern that I mentioned earlier. And there's nothing surprising over there actually. As the aggressor row stays active longer. Okay. So the first observation is that as the aggressor row stays active longer, the worsening trend is consistent across all tested DRAM rows. And when we make the pre-charge time longer, we observe the opposite effect as expected. So fewer DRAM cells experience bit flips, and they experience bit flips at higher activation counts. So it makes more sense to keep the bank pre-charged for a longer time in this case. And this vulnerability consistently reduces across different DRAM rows as well. And yeah, again, you can find more results in this paper. And this is the paper that is you can consider it as a spin-off or follow-up of this analysis that Hasson led, and finally actually found a new read disturbance phenomenon called raw press. It turns out that what we observed as characteristic or sensitivity of RowHammer to access pattern was actually like in the lower level a different type of read disturbance phenomenon that actually led to these change in the vulnerability.
Wait, don't go yet.
Sure.
Can you go back? I'm still trying to parse these observations. This is all about the previous effect that you show.
So the first one is about the previous one. So
okay, but the other ones are?
It's the opposite access pattern. You keep the row closed longer time.
Okay. Okay, I see. Okay, so it's not surprising. Compare when once you know the previous observation.
Yes, they agree with each other.
Okay, can you go back to the previous slide then? So what's interesting about 34.5 and 154.5? Like, why do you have these boundary conditions in the testing?
Yeah, good question. So 34.5 is it was the minimum for these DRAM chips that if you wanted to obey the timing constraints of the DRAM chip itself. So for charge restoration, you need to wait for that amount of time. If you wait less, then it's basically some illegal operation. So we started from there. And then there is no real like upper limitation actually for that, but within the limited time window of executing this project, we only swept until 154.
Mm-hmm.
So we observed some limited aspect of that. So it would be necessary to actually scale it more until like several microseconds at least.
And that's what RowPress did.
Yes, that's what RowPress did.
But were there any infrastructure limitations to go to scale to like microseconds or milliseconds?
Only experiment time. Mm-hmm. So if you consider that infrastructure limitation, yes.
Well, I mean, that's more of a time limitation, right?
Yes.
Infrastructure. Okay.
Other questions? Okay, yeah, this is that RowPress paper. And in RowPress paper, actually, it's shown that you activate this row, and then you don't close it. You wait very long time, around like 30 milliseconds, and then you can reach bit flips with like one activation count. So it's quite impressive. And here, it's just a summary of RowPress from RowPress paper. Instead of using a high activation count, if you increase the time that the aggressor row stays open, for example, instead of 36 nanoseconds, if you wait for 7.8 microseconds, then you can reach read disturbance bit flips at 5,000 activations instead of 47,000 activations. So it's almost a magnitude of reduction in the an order of magnitude reduction in the hammer count. And if you wait for 30 milliseconds, which might not be practical in commodity systems, but it's still showing the boundaries of this phenomena or effect significance of this phenomena. Only one activation is enough to induce bit flips. And yeah, this is the paper. I recommend you to go check it. And this is the third aspect of our characterization, victim cells physical location within DRAM chip. So it comes to your question about the region of the memory that you conduct the attack on. So we observe that RowHammer vulnerability significantly varies across DRAM rows and columns, and we suspect that this is because of the design-induced variation and also because of the manufacturing process-induced variation. And when we look at the minimum activation count to observe the first bit flip or HC first, it exhibits a diverse set of values across rows in a given subarray. But when you look at distributions across subarrays, in a DRAM chip, you see some similar distributions. So here is a distribution S-curve. So on the x-axis, we look at the percentiles of the rows. And on the y-axis, we look at the minimum activation count to observe a bitflip or HC first. So the DRAM rows are sorted by the HC first value, so that we can see this distribution. You can also consider that as some sort of cumulative distribution function. What is important in this plot is that if you look at this dark purple curve, there's a large variation between the highest HC first value and the lowest HC first value that we observe in this chip. Actually, yeah. And when we look at this distribution across different modules, across different manufacturers, we always see some large variation. And therefore, RowHammer vulnerability significantly varies across DRAM rows. So this is the same curve, but we only zoom into the last 10 percentile from P90 to P100 here, as HC first decreases. So this is the worst. This is the 10% of the rows that we observe the worst RowHammer vulnerability. And we still observe some significant variation, about 2x. And we observe that a small fraction of DRAM rows are significantly more vulnerable to RowHammer than the vast majority of the rows. So this is a heat map of bit error rate across columns. So with different colors, we see the bit error rate. And the x-axis shows the column index in the chip, and y-axis shows the chip ID. So it's not, there's not much we can see actually from this plot. I only wanted to highlight that some columns are significantly more vulnerable to, or they exhibit significantly larger bit error rates compared to other columns. This is some aggregated value across rows. And we look into to make some sense out of this observation. We look into the vulnerability level across columns and the variation across chips in a module. So this is some normalized plot. On the y-axis, we have the RowHammer vulnerability worsening as we go from bottom to top. And on the x-axis, from left to right, we have larger variation across different DRAM chips in the same DRAM module. And we observe that there are some columns that show higher RowHammer vulnerability. And since on this leftmost point here, there is like almost no variation. We observe that these columns that are highly vulnerable to RowHammer this vulnerability is coming from some design decisions because it's common across all chips in the module. And when we look at the rightmost point, we observe that there is some high variation in the vulnerability across chips, and this can be caused by the manufacturing process variation.
So I'm trying to understand what x-axis represents. Does it represent the variation across columns?
For a given column, variation across chips in a module.
I see. Okay. So you're really looking at whether that column
yes
becomes worse or has. I see. You're looking at whether that column is has worse vulnerability compared to other columns.
Yes.
And that doesn't change across chips. If
yes.
It's 0.0.
Yeah.
Okay.
So you can also think it like the y-axis is like the mean vulnerability across all chips, and x-axis is more like the standard variation in a normalized way.
Yeah, that didn't help.
Yes. Okay.
I was looking for a more intuitive explanation.
Yeah, for each given, it's like
I understood. Yeah. I understood in the end, but maybe there's a better way to explain these things. I think it's fascinating, basically, to have some columns that are commonly, let's say, highly vulnerable,
Yes.
and some other things that are not vulnerable. It's kind of expected, but yeah.
It's interesting to see that in real chips.
Yeah. And these are columns.
These are columns, yes.
Okay. Not rows.
No, when we look at the bit error rate in a column, we aggregate the bit flips in all rows for that column.
Yeah. Does it make sense to look at rows?
Well, we also looked at the rows in the previous
one, right?
Yeah.
Okay.
Also in our last work as well. It was more row oriented.
Yeah. Which variation is more dominant?
I would say rows is I'm not sure if it's more dominant actually. I need to check the data, but it's more useful in my opinion because all the accesses are in row granularity and all the defenses are working in row granularity.
I mean that's true, but if it's a column that's making it fail more,
yeah,
then it becomes more interesting to profile the columns and then infer the vulnerability of the rows, right?
That's true. Yes, it can reduce our test time.
Yeah.
Yeah.
Because if you look at the latency works, which you were a part of, some of which, it's very sensitive to columns, right?
Yes.
Particular columns that determine the latency. If it's similar here, then it could reduce the testing time.
Yeah. For latency, I can easily reason about that because it can be intrinsic characteristic of the sense amplifier or the bit line. But for read disturbance, I cannot make that explanation. So
yeah, I mean, but you see that 16.
Yes.
There's some empirical evidence that their columns matter.
Yes, that's true. So based on this, we also propose in this paper to craft some particular ECC path schemes so that they will consider different columns with different probability of bit flip occurring. But yeah, we didn't discuss that test in time.
Yeah, that's an idea.
Yes. So we are revealing ideas.
Okay.
On YouTube audience.
Yeah, we need a lot of people looking into these topics, I think.
Yeah.
Go ahead.
So when we look at this analysis across different manufacturers, so not all of them show the same behavior actually, but for example, in manufacturer A and D, we see more variation across different chips. And for manufacturer B, we mostly see the vulnerable columns being vulnerable across all chips. So
yeah, that's very interesting, I think.
Yeah. So maybe Samsung needs to revise their design.
Well, maybe the opposite is true. I mean, if I want variation, I would prefer design-induced variation, though.
So that you know about that.
I know about it, I can control it better, right?
Yes, that's true. Yeah.
Random variation is always tough.
But ECC works well with random variation.
But then the problem is how strong your ECC should be, right?
That's true. If you have too many bit flips, yes.
Yeah.
Okay. So yeah, we conclude that both manufacturing process and design can affect the DRAM columns RowHammer vulnerability. We also look at how the minimum activation count at which a victim row experiences bit flip across, how it varies across rows in a subarray and across subarrays in a DRAM module. And we conclude that the most vulnerable DRAM row in a subarray is significantly more vulnerable than the other row in the subarray. So we have some significant variation across rows within a subarray. And when we compare the AC-first distributions across subarrays, we observe some similar distributions across subarrays in a DRAM module. And they are often distinct from subarrays from different DRAM modules. So we have all these data in the paper, so you can check it. Yes, please.
It's a good question regarding the manufacturer B. Do you think it's likely that manufacturer B is intentionally designing the chips so that they can know which columns are vulnerable and then retire cells accordingly? Is it intentional? Would it be intentional?
So, I mean, to implement more than necessary number of columns and rows, and then retiring some more vulnerable columns and remapping them to these like extra columns, or the same for rows. That method is common across like many manufacturers actually. That's used for improving the yield, so that you can ship out more chips in a higher throughput, and you ensure the reliability in a better way. But I'm not sure like if they're doing this like particularly for the disturbance. So it's a complete unknown, and it's a black box for me. Yeah, because we do not know the insights into their design decisions. Yeah.
So, did you do any reverse engineering for logical to physical column addresses? Because we know that in row addresses we need to do logical to physical.
Yes.
So here, how did you do any reverse engineering, or?
No, we did not do that.
I see.
I'm actually not sure how we can do that.
In PARB, I guess there's a paper called PARBer that shows how you do like methodological.
Oh yeah, that's right. So we didn't do it here. We
So
just
these are all based on memory controller visible addresses.
yes.
So that's what you consider a column.
Yes.
Internally, the column may be remapped somewhere to another column.
Yeah.
But even then, we don't know how a column is mapped physically to the chip. So if you do that,
You mean across maths and
a physical column worth of data, how
Yeah.
is it distributed to the chip?
And that's not possible to reverse engineer.
Difficult, I don't see a way, clean way right now.
so I guess data pattern dependence can give some idea to some extent, but
And that's what Harbor tries
Yeah.
to do, right?
yeah,
Those are
that's
tough
why I said
experiments,
that.
but yes, you need to invest a lot of time to do those experiments.
Yes.
Because for rows, there's always one physical row that looks like a horizontal bar. But here, a column, we don't know, like it's where the cells are coming to make up that column.
But what does that mean for these results? That means like this 50.8% is pretty strong then, even without any compensation for those cases where things may be remapped, you're still seeing a 50.8%.
That's true. Yes.
Fraction of columns that are pretty bad, right? Consistently across different chips.
Yeah. It's basically the same logical column ID across different chips.
Yeah.
Even if it's not. Yeah.
So maybe that number is even higher.
Could
if
be.
you account for.
Yeah, if you reverse engineer that, yes.
Yeah, if you look at the physical picture.
Are there other questions?
Maybe I can ask later.
Okay. So I will go with.
I'm not going to repeat my question about what are the implications of this. What am I going to do with this, right? I'm curious, but you want to keep the suspense. Just make sure you don't forget by the time you reveal what you're going to do with this.
No, I have slides for those. So the next thing is the voltage sensitivity of RowHammer. So here, okay, here's a little more background. So in DDR4 DRAM chips that we test, we have two main voltage sources. One of them is called VDD. It's around 1.2 volts, and it's supplying power to pretty much everywhere in the chip. And there is another power rail called VPP, and it's around like 2.5 volts, and it's exclusively for the word lines. That's for row activation. And VPP is significantly larger than VDD, so that the access transistors can conduct well because it's connected to the gate of the access transistor, and it's important for creating a strong channel between the capacitor and the bit line so that you can conduct well. And when we look at this VPP, so this is another cartoonish picture of RowHammer again. So in that plot on the right top, we have time going from left to right, and we see the aggressor row's wordline voltage on the y-axis. So when we activate the aggressor row, we assert this wordline with high voltage, and then it creates that kind of jump over there. And then when we close it, the voltage goes low. And then we activate again, voltage goes up, and then go low, and then goes up, and then go low. And then we observe bit flips in nearby cells. And essentially what causes this bit flips is repeatedly toggling this wordline voltage here. It's a key to induce these RowHammer bit flips. But it was not studied before how much the magnitude of this voltage affects the RowHammer vulnerability. So our hypothesis is that when we reduce the wordline voltage, we can reduce the RowHammer vulnerability, and it can come with create a weaker channel in the access transistor, but we are not expecting it to significantly affect reliable DRAM operation. So our goal is to understand how the wordline voltage affects the RowHammer vulnerability and reliable DRAM operation on real DRAM chips. So for this study, we tested this set of DRAM chips from 3 manufacturers. It's again more than 200 DRAM chips, and they implement different densities, die revisions, organizations, and they come from different manufacturing types. And we have more detailed information about every single chip in the full paper. So our first takeaway is that reducing wordline voltage reduces RowHammer vulnerability because you have lower fluctuation in the wordline voltage, and it can cause fewer bit flips, and it increases the necessary hammer count to induce bit flip by some amount. And here is some data. On the x-axis, we look at the wordline voltage. So 2.5 volts is the nominal voltage, and then we reduce it from right to left. And on the y-axis, we look at the bit error rate. In this case, lower is better. And we observe that there's a dominant decrease in trend here. So here, every curve represents another DRAM module from this manufacturer. This is a plot from manufacturer B. And the shade around the curve shows the variation across different DRAM rows in that DRAM module. And we observe that bit error rate reduces as VPP reduces, or wordline voltage reduces. And there are also some corner cases where bit error rate increases as voltage reduces. So reducing wordline voltage can cause more DRAM cells to experience bit flips in a small fraction of DRAM rows. And when we look at these two observations across 3 manufacturers, we observe the same behavior in all of them. Yeah, here. Okay. So the next thing is, again, with varying wordline voltage, now we look at the minimum activation count to induce the first bit flip. So in this case, higher is better because when we need higher number of activations, it becomes harder to induce these bit flips. And again, different curves identify different DRAM modules, and the variation is across DRAM rows. And we observe that the first bit flip occurs at higher activation counts as a dominant trend as the wordline voltage reduces. And there's also some points below 1.0. So a minimum activation count induced the first bit flip can reduce as well in corner cases. And as for a small fraction of rows, the first bit flip occurs at a smaller activation count. And again, for these two observations, when we look at all three manufacturers, the general trend is pretty much consistent across all of them. So we also look at the wordline voltage effect on RowHammer vulnerability across different DRAM rows and manufacturers. And we observe that the change in bit error rate varies across different DRAM rows and manufacturers. And the change in HC first also varies across different DRAM rows and manufacturers. So it's not, again, like super straightforward relation. You can see more data about this analysis. So the key takeaway from our RowHammer analysis for reducing wordline voltage is that when we reduce wordline voltage, it reduces RowHammer vulnerability as a dominant trend. So what about the other operations that we perform in DRAM chips? Because there was this chance of creating a weaker channel, and it can potentially affect the reliability of the DRAM chip. So we observed that most of the tested DRAM chips still reliably operate when we reduce wordline voltage by using nominal timing parameters. And for the remaining chips, if we increase the activation latency a little bit, they can still reliably operate. And we also look at the how the retention time changes. And again, most of the DRAM chips can work with nominal refresh rate. And for a small fraction of them, we can implement some singular correction codes to compensate for the effect of reducing wordline voltage. Or we can just double the refresh rate for a small fraction of DRAM rows to compensate for it. Okay, so let's look at some data. So here in this plot, again, we have the wordline voltage on the x-axis, reducing from right to left. And on the y-axis, we look at the minimum reliable row activation latency. So again, different colors show different DRAM modules, and we look at the shades show the variation across different DRAM rows. And we observe that the row activation latency increases with reduced wordline voltage, so it's something bad. But also, there is some nominal activation latency that is defined in the data sheet of the module, and it's already significantly higher than the actual activation latency that we observe. And this has some significant guard band. And even though this increase happens in the row activation latency, when we use the nominal activation latency, most of the DRAM modules chips can still reliably operate. And this is again a common trend across all DRAM manufacturers, all DRAM modules from all facet DRAM manufacturers. And so when we look at the latencies above the nominal TRCD or row activation latency, we observe that 48 DRAM chips from manufacturer A reliably work with row activation latency of 24 nanoseconds. So from 13 to, we need to increase the activation latency to 24 nanoseconds for those rows in those chips. And for 16 DRAM chips, this value goes to 15 nanoseconds from 13 and a half, if I remember. And for manufacturer C, you don't need to even change nominal TRCD. All chips, all tested chips already work. Okay, so to understand a bit more how this phenomenon occurs, we look at the we conduct some SPICE simulations, and I'm not going to go through the circuitry. I just put it there because it's cool, and we look at we conduct SPICE simulation using these parameters using a 22 nanometer transistor model. And we conduct a Monte Carlo analysis where we introduce 5% variation in the parameters of this circuit model across 10,000 iterations. And we observe how the row activation happens. So on the x-axis, we look at the time, and on the y-axis, we look at the voltage on the bit line. So the row activation happens when the bit line voltage reaches to this threshold voltage that is defined over there. And and here different colors show the curve for different wordline voltages. And we observe that as we reduce wordline voltage from 2.5 volt down to 1.7 volt, we see a shift from left to right at the cross-section of this curve to this threshold voltage, meaning that row activation process completes later as we reduce wordline voltage. And this is because of this access transistor. Reducing the wordline voltage causes a weaker channel. And the row activation latency increases as a result of reducing the wordline voltage. And okay, so this is showing the this is a probability density function that shows the minimum reliable row activation latency across all our iterations in the Monte Carlo analysis. And different curves are corresponding to different wordline voltage levels. So the leftmost yellow one is for 2.5 volts, which is the nominal voltage. And as we go right, actually, you can see that the voltage decrease. As the voltage decreases, we go the distribution go from left to right. So the activation process takes longer. So this is the nominal row activation latency at 13.5 nanoseconds. And when we look at the worst case TRCD, which is the tail of the curve, tail of the distribution for the wordline voltage of 1.9 volts, it's still under the nominal row activation latency. And when we look at the worst case for 2.5 volts, it's again lower than 13.5 nanoseconds, but the gap in between is larger in the nominal voltage compared to the reduced voltage. So we do not lose reliability by exceeding the nominal timing constraint, but we sacrifice some of the guard band that we have in the nominal timing constraint. And we conclude that Spatial simulation results also agree with our observations. Of course, these simulations are not using the exact same parameters for as our DRAM chips have, because we do not have those numbers. But if you look at the general trend, it's the same thing. Sure.
How do you determine 12.9 nanoseconds is the worst case latency? Because I know the testing infrastructure supports increments of 1.5. Did you test with a 12.9 nanosecond latency? Were you able to do that?
This is not real experiment, right? This is just Spice mode.
Okay,
Yeah. Yes.
Okay. Have you checked TRS or TRP?
So TRP is not that relevant because it's just about the pressure circuitry and the bitline capacitance, and it doesn't change with the wordline voltage. And we looked at TRS and its effect on the data retention time as well.
Do you have a similar plot for experimental data? The probability function. I mean, it won't be PDF in that case. It will be real data.
So we have data across different rows. I'm trying to remember if you plotted it. Maybe not.
I was going to ask, but does it look as nice as in the Spice results, like the distribution, normal distribution?
I need to double check.
But this is just like out of curiosity.
Well, I had the same question actually. The first question you had, which is, do you have the plot for the real data? It'd be good to plot it. I don't think it's going to look as nice, but
Yeah, for this distribution.
Yeah, for that
Like,
distribution. That's a good way of looking at it. Right?
yeah. Yeah, I have the minimum, maximum, and average, but I don't remember plotting the whole distribution. Yeah.
The issue there is like the latest values you can test are very small, not in numbers.
Yes, yes. It's just like 1.5 nanosecond steps, right?
But still, that could be good enough, right?
Could be 3 bars
That's true.
or 4.
Yeah. The range is not that large.
Yeah, yeah.
Okay. So we also looked at the wordline voltage effect on DRAM charge restoration process. That's your question. So we observed that when we reduce wordline voltage, the capacitor voltage can actually saturate at a lower voltage level than it saturates when the wordline voltage is nominal. And this is because the gate to source voltage difference in the access transistor is lower. So if you consider like it goes to full VDD, for example, it cannot go, right? Because like as you reduce the gate voltage, the source, the channel disappears after the source voltage reaches to some lower amount, and then it saturates over there. And this can cause some reduction in data retention time as well, right? So, and we also observe that the charge restoration latency can increase in those cases, even if like saturation is not happening at lower place, because the channel is weaker and it conducts less, so it flows in at a longer time. Okay, so yeah, I don't have those results with me in this presentation, but we can look at them later offline. And you can also see them in this paper. Okay, so now we will look at the how it affects the nominal refresh rate. Here in the x-axis, we have the refresh window going from 64 nanoseconds to 16 seconds. 64 milliseconds to 16 seconds. I guess I said nano. And on the y-axis, we look at the data retention bit error rate. Not surprisingly, for all different voltage levels, we have some exponential increasing curves, right? With the increase in refresh window, because it's general behavior of volatile DRAM technology. And the interesting thing is, not interesting actually, it's not surprising, but the thing that we observe is that when you look at the different colors, they correspond to different voltage levels. And you can see that the yellow curve is at the bottom. And then as we reduce wordline voltage, the data retention bit error rate increases. So the volatility increases in a general sense. So more DRAM cells tend to experience data retention bit flips when wordline voltage is reduced. We observe that when we apply the nominal refresh window, which is 64 milliseconds in normal operating temperatures, we observe that most of the DRAM chips still reliably operate without experiencing data retention bit flips. And we observe these observations across DRAM modules from all three manufacturers. And when we look at the distribution of these data retention bit flips, we observe that when there's a bit flip at the nominal refresh rate because of the wordline voltage reduction, it happens like, so a given 64-bit word at most have one bit flip. So this means that the data retention errors can be avoided by employing some singularity correcting codes for the smallest refresh window that yields non-zero bit error rate. So here we have that distribution actually. So on the x-axis, we have the number of 64-bit data words with 1 bit flip. And on the y-axis, we look at the fraction of DRAM rows. How many rows, how much of the rows have this kind of data words? And we observed a small fraction of DRAM rows contain erroneous data words because most of them are accumulated at 0. So it's really rare to see these bit flips. Yeah, so, okay. I forgot what I was going to say, but I'll just go with the observation. Only a small fraction of DRAM rows have erroneous words at the smallest refresh rate. So this can be 64 millisecond or 128 millisecond, depending on which DRAM module you're looking at. But this is the minimum refresh rate that yields non-zero bit error rate, and for these refresh rates, you have only a small fraction of DRAM rows that have erroneous DRAM words.
At what voltage level is this result?
So it's actually not the same voltage level for all modules. So for each of them, we look at the minimum voltage that we can go. For some of them, it's like 1.7 volts. For some of them, 1.9 volts.
Okay.
2 volts.
Okay.
Because after
so this is the worst possible case that you tested.
Yes.
For each
module.
So are there voltage levels where you get all 0-bit error rates, reduced voltage levels?
Probably. I need to check that.
You have the data probably.
Yes, I should have that data. On top of my head, I can, I guess, confidently say that at 2.4 volt, 2.3 volt, like very close to nominal voltage, you don't see any bit flips. But I'm not sure like how long it gets. I need to analyze it.
Basically, what I'm getting at is, do you really need to go all the way to the lowest voltage levels? Is there a compromise where you go to a middle low voltage level and you reduce the vulnerability a little without impacting data retention or latency?
Yeah, we can find some sweet spots like that. So another general takeaway we get from this work was that yes, we reduced the RowHammer vulnerability, but the reduction is not really strong, even when we go to like very low wordline voltage. So in the middle, it will be even like weaker reduction.
Yeah.
So if it affects the disturbance, sorry, if it affects the data retention time less, then it affects the data disturbance as well.
Yeah.
Data disturbance.
Okay.
So at the end, these are the two takeaways from the wordline voltage's effect on DRAM operation. We observed that most of the DRAM chips reliably operate at nominal timing parameters and at nominal refresh rate. And for the ones that do not work reliably at those levels, we can just increase the row activation latency a little bit, or we can implement some singular correction code or double the refresh rate for a small fraction of DRAM rows that exhibit those erroneous words. Okay, this is just a summary of the takeaways. It reducing wordline voltage reduces RowHammer vulnerability. It comes at the increase of row activation latency and reduction in the data retention time, but we have ways to compensate for that. And this was our hypothesis. Reducing wordline voltage can reduce RowHammer vulnerability without significantly affecting reliable DRAM operation, and we showed that through real chip experiments. And this paper was published in DSN 2022. You can go check and see more in-depth analysis. So yeah, I covered everything regarding the RowHammer characterization. So I will talk a little bit about the implications. So I will just go over like, yeah, first I wanted to say that our observations can we leverage to craft more effective RowHammer attacks and more effective and efficient RowHammer solutions. And I'll go through 2 attack improvements and 1 defense improvement, and then I will refer you to the papers for more information. So this is about the temperature sensitivity of RowHammer. So let's say your temperature is around 70 degrees system, and this is coming from the real chip experiments from manufacturer C, which is Hynix. We observed that 76.6% of the tested cells exhibit RowHammer vulnerability above 70 degrees Celsius. So if you look at those DRAM cells, you make them victim cell and then you attack them. If you observe a bitflip, you can understand that the temperature is above 70 degrees Celsius, right? So you can identify some abnormal increase in temperature to attack a data center during its peak hours. Or you can use this. We also had the observation that there are some very small fraction of DRAM cells that exhibit RowHammer vulnerability only at particular temperature levels, like 70 degrees. At 70 degrees, there's only like 0.4% of the tested cells exhibiting RowHammer vulnerability. So you can use this to precisely measure the temperature to trigger an attack, and exactly at the desired temperature. And based on that, actually, there is a paper on arXiv, and I assume it will appear in IEEE Access sometime soon. SpyHammer, led by Luis Orosa. So you can go check this paper. It's available online on arXiv already. It shows how you can spy on the temperature using RowHammer. And about the memory access pattern sensitivity of RowHammer, instead of activating aggressor rows as frequently as possible, you can just keep the aggressor row active for a longer time in your access pattern, so that you can reduce the necessary hammer count to induce a bitflip significantly. And if the deployed RowHammer defense on that system doesn't account for this, you basically bypass this mechanism, right? Because your threshold is different now. And RowPress actually shows this. You can ask Ataberk about the real system experiments and how they bypass the existing mitigation mechanisms using RowPress to induce bitflips. Okay, so as an example of defense improvement, we observed some significant variation in read disturbance vulnerability across DRAM rows. And a key idea is to dynamically adapt the aggressiveness of existing solutions to the victim row's read disturbance vulnerability. So how you can do that? Basically, you know which row is under attack, and you know the read disturbance vulnerability of that row. So you can make the existing RowHammer solution more aggressive or less aggressive based on the profile that you have. And we actually looked at some state-of-the-art RowHammer defense mechanisms, Aqua Block Hammer, Hydra, Para, and RRS here. And we observed that as minimum hammer count to induce first bitflip on the x-axis goes lower from left to right, these mechanisms observe some significant performance degradation because of aggressively mitigating RowHammer attacks. But by using this profile that you have, you can actually reduce their performance degradation significantly, and you can make them work even at a threshold of 64 activations in a practical way. So this is a paper that will appear in HPCA 24, so I will not go through it in a more detailed way in this talk, but we can do that in the talk on Monday if you prefer.
Yeah, I think that'd be good.
Okay. Okay, so in the full paper of deeper look, we actually suggest some more defense improvements. So we can, for example, leverage the similarity across subarrays in the DRAM module to reduce the testing time or profiling time of DRAM chip, if you sample a few different subarrays, there are hundreds of them in every bank. We know that the behavior of the distribution of thresholds across subarrays are similar to each other. We can get some rough idea about the vulnerability level of the DRAM chip. So we can monitor and limit the the time that a row can be kept active from the memory controller, for example, so that we can reduce the RowHammer vulnerability to make defenses more efficient. Another thing that we talked about already is we can design new ECC schemes that can target the non-uniform bit error distribution across different columns. And from the temperature analysis, at least for the manufacturers other than Samsung, we know that cooling DRAM chips can reduce overall bit error rate. So these are the defense implications that I wanted to cover, but more is, of course, in the full paper. So in conclusion, we tested 272 DRAM chips from 4 major manufacturers. And our key results show that a RowHammer bitflip is more likely to occur in a bounded range of temperature if the aggressor row is active for a longer time in certain physical regions of DRAM module compared to the other physical regions, and when the aggressor row is activated using a higher voltage. And in conclusion, our observations can inspire and aid future work to craft more effective attacks, as we see in SpyHammer, or design and RowPress as well, and or design more effective and efficient defenses, as we saw in the paper that that will appear in HPC 24. Okay, so I'd like to also take a few more minutes to talk about some future research on RowHammer characterization. So the first one is the effect of aging. So this is still not known, and there's more research that needs to be done. So in our recent experiments, we observed that this is a preliminary data on just like aging via 68 days of hammering. So it's not really a rigorous aging study, but we observed that this plot basically that I will explain. So on the x-axis, we have the minimum hammer count to induce disturbance bit flips, or HC first, before aging. And on the y-axis, we have the same parameter after aging. And this black line shows y equals to x. So the points over there are just showing that, you know, the result is repeatable after this aging. But there are some points in the triangle below. And these rows show that by aging, it's possible to reduce HC first. So since this is not a rigorous study, I do not want to make a strong claim, but we can see that aging can lead to redisturbance with flips at fewer hammers, and there's definitely more research needed in this direction. You can see this paper for more results.
Can you go back to that? I think this is very interesting, certainly. I mean, even if it's not a full aging study, it shows that there's an effect, and that's enough. That's enough for
motivating the future work.
Not motivating the future work, but also worrying, right?
Yes.
Meaning everybody tests these DRAM chips offline statically. They find some magic RowHammer threshold, and you come here and just test it for 68 days and show that things vary. In some cases, pretty significantly, right? Something goes down to 64K from 96K, for example, right?
Yeah.
And even it goes down from 12K to 8K over there, I think.
Yes, yes. 0.4%.
And it's only 68 days. 68 days is nothing.
Yeah. So with more rigorous study, probably we can show more reduction.
Yeah.
Hopefully.
I think that's a big cause for alarm. So it's good to. So you have this study in this SWART paper at HPCA.
Yeah, this preliminary one only. Yeah.
Okay.
And
there's something you should correct, at least in this picture. I think the y-axis label also reads before aging.
Oh, sorry. It's after aging on the y-axis.
Okay, that should be y-axis is after aging, right?
Yes.
Not the x-axis.
Yes, yes.
I hope. Okay.
Yeah, y-axis is after aging.
So hopefully they don't get better with aging. Are there cases where they get better?
Not that I saw, but could be. I don't know.
Okay. Well, not in this. At least empirically, you don't see it after 68 days in any of these chips.
Is this one chip or?
It's one module. Yeah.
How many times did you repeat for both cases? Or like it's like you analyze the entire data gathered over 68 days?
So it's a good question. So these are coming from, again, like 10 times of repetition. And the second one is also true because I was conducting RowHammer tests all this time. So yeah, I looked at the data.
So it's like okay, so for the reduction, do they appear on the same row?
Yes, this is like, yes. So this is a bubble plot actually that I forgot to tell. So the size of the circles are showing the population of DRAM rows in that region. So if you look at like, I don't know, 96K on the x-axis, so 1.3 plus 98.7 sum up to 100%, right? So it's like 100% of the rows that observe 98K RowHammer threshold before aging, and only 98.7% of them exhibit 96K HC first after aging. So 1.3 goes down to 64K. So it's like the same row goes from 96 to 64. And this is also a coarse grain, so they could be going some middle points as well. I just tested these hammer counts for this study, so it's not really a precise AC first as well, but
okay.
Yeah.
But it shows that there are a small number of rows. Well, maybe not small because there's also like 9.1, right? So that's a large number of rows that reduces HC first significantly.
yeah.
And why is there like only two values per, let's say, x-axis value? So it's like 64 the minimum, or it's like some arbitrary chosen?
So it's like both before aging and after aging, I test all those rows at all those hammer counts. This is just some empirical observation that we see that only 2 points appear at every x-axis value. So I have an explanation for that. And for example, if you look at the rows at 32K or 128K, they don't change, right? There's only like 1 point. So
okay, so
there's no like, there are no 3 points at an x-axis value.
So the reason for no 3 points is because like a plotting issue, or like you don't fully analyze all the data?
It's not it's neither of them. It's just like empirical data shows this.
Okay. But why though? So like, does it imply like there are some, let's say, how to say,
I think this study is not as rigorous to imply anything.
okay.
So it's just motivation for like future work on aging.
It shows that there's signals.
Yes.
And what's the temperature that you keep the module at?
80 degrees.
80 degrees Celsius. Okay.
Yeah.
And do you continuously keep hammering for 68 days?
Yes.
Yeah, that's another issue, right?
So it's not a methodical way of aging as well, actually.
It's like
it's
more
just
hammered aging.
Yes.
You keep hammering while aging.
So it makes sense because activating a row is really a power hungry process. So it can cause a lot of charge going across the chip, but I mean, yeah, it's not really the conventional way of doing the aging.
But still, I think it's interesting, and it's still a cause for alarm.
Yeah.
And more studies.
Yeah, it also motivates that there's need for some fast profiling methodologies so that we can keep doing the profile online and keep updating our reliability profile.
Yeah.
But currently, it's just too expensive to stop the operation of a DRAM chip and then do the testing.
Well, we don't know if we need that yet, right? Because if you do that more rigorous study and find out we can model the aging's effect somehow, you don't need to compile online, you just have to.
Yeah, if you can do that, yes, but I'm not sure if you can do that. Okay, I'll move on. So another future research that will be interesting for RowHammer characterization is to understand interactions across different DRAM error mechanisms. So we know RowHammer since 2014. We recently learned about RowPress, but there are also other error mechanisms that take place in DRAM chips. Data retention times is very straightforward one. Variable retention time is still a mystery that needs to be solved. More characterization is needed to that, and also we need to see the interactions across them and their like cumulative effect on the system reliability as well. So maybe your system is not vulnerable to RowHammer that much at some point, and then variable retention time also adds up, and then you are suddenly more vulnerable to RowHammer. Things like this should be investigated more, in my opinion. But this is really, there is also another really important question. So what is the worst case? We still do not know. So in this characterization studies, we looked at the effect of temperature, data path. Well, I didn't show the effect of data pattern, but in these studies, we also looked at the effect of data pattern, memory access patterns, spatial variation, voltage, and not all of these have some straightforward relation with the RowHammer vulnerability. If you take temperature, you need to test all temperature levels for all DRAM cells to say if a DRAM cell is vulnerable to RowHammer at some configuration, right? So it's not clear what is the worst case, considering all these sensitivities. And it's also not clear, like, what is the minimum hammer count to induce the read disturbance bitflip? And this is important because it is used as an input for your solutions to configure, and you get this as a threshold value for the activation count, and then you configure everything of your solution based on this value. But if this value is a lie, then your system is not reliable anymore. So it brings the question, how reliable are our DRAM chips? And more importantly, how reliable will our DRAM chips be tomorrow? So these are important to understand. And I think we need more research on this direction. And as a reminder, my thesis statement was building a detailed understanding of DRAM read disturbance and leveraging insights into modern DRAM chips and memory controllers enable researchers and engineers to mitigate DRAM read disturbance efficiently and scalably. And we covered the studies for the orange part, building a detailed understanding of DRAM read disturbance. And on Monday, we have another talk that we will cover the solutions to DRAM read disturbance. So I hope to see you there as well. And this concludes my talk. Thank you very much.
Are those pictures lanes of swimmers? Previous slide. Go to the previous slide. Yeah, the swimming analogy and this paralyzing preventive actions are swimmers.
No, not really.
No, it doesn't work.
In my imagination, it was like the timeline on the x-axis.
I figured, but
yeah.
Now your task is to tie it to the swimming analogy.
Maybe, yeah.
And also for the leveraging interrogated is like a swimmer going across multiple lanes.
Yes.
Very, very, and not polite at all.
Yeah, you don't want to be in that swimming pool.
Yeah. So interesting. Okay. Are there more questions, discussions?
Anyone online? Do you have more questions?
I guess that's it.
Yeah, I think we're done then. We'll continue this. Is that Monday? 5 days later, 22nd of January. Okay, thanks, Giray.
Thank you.